Hello there, this is Kai with the CHS Math team, and today we're going to be looking at some pretty cool properties of the GCD and LCM functions. And these are probably some of the most important functions pertaining to number theory, so looking at some of their properties is also really important. So the first property they're trying to prove is that for two positive integers a and b, when you multiply a and b, it's the same as multiplying their greatest common divisor and their least common multiple. And here, what we're saying is that for the greatest common divisor of a and b, if we multiply a and b by the same constant, that constant can sort of come out on the other side of the function right here. And this almost feels like it should be some sort of distributive property, but obviously this is a function, so it doesn't exactly work that way, so we're going to have to prove it differently. So we'll get to that in a bit, but first things first, we're going to focus on this function right here. So the way that we're going to prove this is using a and b as 18 and 30. So we're also going to need to find the greatest common divisor of these two numbers and their least common multiple. So I'll just do that over here. And then the least common multiple. And then we're also going to apply one constraint to our answer, which is that everything on this side is going to be a prime factorization. So we can start by just finding the prime factorizations of 18 and 30. So 18 and 30. So 18 splits into 9 and 2, which then splits into 3 and 3. So the prime factorization of 18 is going to be 2 to the first power times 3 to the second power times 5 to the 0 power. Leaving this 5 here, and you'll see why in a little bit. So the prime factorization of 30 is going to be 10 and 3. 10 splits into 5 and 2. So we have the prime factorization of 30 as 2 to the first times 3 to the first times 5 to the first. And you're starting to see why, but this is why I left the 5 to the 0 here. It's more just as a visualization. So then we're just going to copy these down up here. So the prime factor of 18 is going to be 2 to the first times 3 to the second times 5 to the 0. And then we're going to have the prime factorization of 30 as 2 to the first times 3 to the first times 5 to the first. So now we're going to find the greatest common denominator of these two numbers. And what we learned last week is that basically the way you do this is you look at the prime factors, and then you look at the corresponding prime factors, and then you're going to look at their exponents, and then whichever one is lower is going to correspond to the GCD function. So we're just going to go factor by factor here. We're going to start with 2, and since 2 to the first is the same as 2 to the first, it doesn't really matter which one we pick. So let's just grab this one. So we have 2 to the first, and then we're going to look at 3 and 3, and then we're going to look at their exponents, 2 and 1. So 1 is less than 2, so we're going to pick this one right here. And then we have 0 and 1. Obviously, 0 is less than 1, so we're going to pick this one. And then we're going to move on to the LCM function. The LCM function does the same thing, except you're going to take the bigger exponent instead of the smaller one. So we're going to find the 2's. We could pick the same one twice, but just for the sake of visualization, I will just pick this one. And then we're going to move on to the next one, 3 to the second. Obviously 2 is greater than 1, so we're going to pick this one. And then 0 and 1, and then we just pick the 1 since it's greater than 0. So now if you're starting to see the pattern, essentially what we have here is two sets of prime factors here and here. So obviously these factors, these lists can be made if you just multiply 18 and 30. So if you multiply 18 and 30, you're going to get all of these prime factors right here. And then if you multiply these two, then you're going to get all these prime factors over here. And then what we're going to do is we're going to notice that there's a sort of one-to-one correspondence between these. So we have this corresponds to this corresponds to this corresponds to this, and this corresponds to this corresponds to this, and this corresponds to this. So basically what this means is that these two lists of prime factors are actually the same. So basically what this means is that if we combine the prime factors of 18 with the prime factors of 30, by multiplying them, it's going to be the same as the list of prime factors over here, which can be made by multiplying the GCD function of those two numbers with the least common multiple function of those two numbers. So essentially what we've done here is we've just proven our first identity, which states that for two positive integers a and b, that it's the same as multiplying their greatest common denominator with their least common multiple. So basically, with 18 and 30 as our a and b, this proves this identity up here. So next we're going to look at this right here. So I'm going to prove this using the GCD function. So I'm just going to clean up a little bit here. So now the way we're going to do this is we're basically going to rewrite the prime factors of 18 and 30 a little bit differently. We're basically going to expand it. So instead of writing 3 to the second, for example, we're just going to write 2 3s. And then, so first we're going to start with 2 to the first. So then we just have a 2, then 3 to the second, which means we write 2 3s. And then we can stop there. Next we're going to move on to 30. 30 is just going to be 2 times 3 times 5. So our GCD function, essentially what it's going to do here is it's just going to look at the prime factors that these two numbers share. So since they share 2, then the GCD function is just going to be 2. And then since they share a 3, then it's going to have a 3 there. So basically, this is basically what the GCD function is doing. It's basically showing the list of all the prime factors that these two numbers share when you actually expand them. So now what we're going to do is we're going to apply a C value. So basically we're just going to pick some, let's just say 49 as our C. So what this means is that for our prime factorization, the prime factorization of 49 is obviously just 7 and 7. So then it's going to come out on this side, 7 and 7. So what this means is that when the GCD function goes back through, it's going to check all these numbers, and it's going to see that it shares 2 7s. So what this means is that for our new GCD function of 49 times 18 and 49 times 30, it's going to have a value of, it's going to share 2 2s, or sorry, it's going to share 1 pair of 2s, and then they share 1 pair of 3s, and then they share 2 pairs of 7s. Oh, sorry, I'm just going to use a different color here. And then, when we substitute everything out, basically this identity is going to pop out. So basically, we can, oh, sorry, this 3 isn't supposed to be there, sorry. But basically, when you do the substitution, this identity right here is going to pop out. So obviously, 2 times 3 is equal to the GCD of 18 and 30. And then 7 times 7 is equal to 49. And then this basically proves this identity over here. So basically, we have a C and an A, and then a C and a B, same thing as this, and then that's just the same as the GCD of A and B, which is 18 and 30, times the C, which is 49. So we've just proved this identity right here. And then you may be wondering, how do we prove this for the least common multiple function? So the issue with the least common multiple function is that its true meaning is a little bit more difficult to understand almost, because the GCD function has the nice meaning of just sort of matching up all the, sort of just listing all the prime factors that these two numbers share. But that doesn't really work for the LCM function. So the way that you prove this with the LCM function is by just finding the LCM of some a and b. You can just pick any a and b as long as they're positive integers. And then you're just going to set your a and b, find their least common multiple, and then just apply different c values using this identity to just see if it holds up. And I'm not going to do it here because it's going to take a while and it's not a very pretty visualization like this one is. But if you try this at home, you'll see that it does in fact work. So basically this sums up just proving these three identities here, which are sort of core to a lot of number theory and are pretty central to understanding the GCD and LCM functions. So that pretty much sums it up, and have a nice day.